On Earth, we move between points which remain fixed relative to each other. But in our solar system, all bodies are in continuous motion. Man has long observed the movements of the sun, the moon, and the planets. He's measured angles and distances, calculated gravitational forces and the shapes of orbits. His vision was limited only by technology. The sharper tools of the 20th century have allowed him to measure the movements of the sun and the planets with reference to other stars in our galaxy. And now he leaves Earth on journeys into space. Eventually, man will set out toward another planet, millions of miles distant. The instruments and techniques of modern science will guide his spacecraft with an accuracy and precision inconceivable to Earth-bound navigators. Though the spacecraft will be traveling at tens of thousands of miles per hour, it will seem to the men on board to be hanging motionless. For them, the stars will be fixed in their positions. There will be no day or night. The receding Earth will not remain behind them, but will be imperceptibly moving ahead. Where they left Earth, there is now only a point in space. If their objective is Mars, for example, they will not be moving directly toward it, but along a curving path, leading them to another point in space beyond the sun. They must arrive at that point at the same time as Mars. Neither they nor the planet can stop and wait. On this trip, an error in injection velocity at Earth of less than 0.1%, that's about 25 miles per hour, will, if it goes uncorrected, cause the craft to miss Mars by over 1/3 of a million miles. The additional propellant and time required to correct so large an error near the end of the trip might be prohibitive. The mission would likely fail. But errors in spaceflight can be corrected during flight because the principles of space navigation are based on the knowledge that the forces involved are constant and predictable. In our solar system, each planet is locked into its orbit around the sun by its particular velocity, the planet's momentum being balanced by the sun's gravitational pull. The inner planets, where the pull is greatest, travel at greater speeds than the outer planets, where the pull is weaker. If a spacecraft is to leave the Earth for another planet, it must increase or decrease the speed imparted to it by the orbiting Earth. Yet, either way, this velocity change is a fraction of the orbital speed of the Earth, 66,000 miles an hour. The velocity imparted by the Earth also puts the spacecraft into the ecliptic plane. That's the plane of the Earth's orbit. It would take the expenditure of considerable energy to get out of that plane. Fortunately, all planets move in planes very close to the ecliptic, and they all orbit in the same direction. Unlike the planets, a spacecraft can change its orbit and its direction because it can change its velocity. When a spacecraft escapes the Earth's gravity in the same direction as the Earth's travel around the sun, its greater momentum around the sun overbalances the sun's pull, throwing the spacecraft outward. But the sun's steady pull eventually slows the craft's outward flight, and here, unless it can boost its speed, it will start to fall inward. On the other hand, if the spacecraft leaves the Earth at the same speed as before, but in a direction opposite to the Earth's travel, it reduces its own velocity around the Sun, permitting the Sun to pull it gradually inward. But as it falls, it gains speed. This increasing momentum will throw it outward again unless it can reduce its speed. It is a controlled velocity change which alters the course of an orbiting body. In this voyage to Mars, the path the spacecraft should follow has been computed. But putting the craft on exactly the right path cannot be done. Even the most sophisticated launching rocket controls can't avoid small inaccuracies in launching or account for the uncertainties in the orbits of the Earth and planets. There will always be a small error to be corrected. The first correction will compensate for most of this error. A small velocity change made early in the voyage will have a much greater effect than the same change made later. Later corrections will remove residual errors and refine the trajectory of the craft. Fundamental to all navigation is the ability to measure angles. For this, man in space uses a sextant, a device he's been using for over 200 years. With this instrument, the astronaut measures precisely the angle between a planet and a known star. This is recorded along with the exact time of the sighting. This angle defines a cone of position because the angle between the planet and the star could have been sighted from any point on the surface of that cone. But one sighting will not tell him where. The astronaut does know he is near his desired trajectory. His approximate speed, elapsed time, and limits of possible error locate him within a football-shaped volume which navigators call the estimated ellipsoid of position. The space where this ellipsoid intersects the cone establishes his position more closely, in an area where the two coincide. From this, he knows about how far he is from his desired trajectory. Repeated sightings will be made to reduce the amount of uncertainty until the actual trajectory is determined within the allowable limits. If it does not coincide with the desired one, the astronaut must perform a mid-course correction to put his craft on a corrected trajectory. A more precise method for determining position uses 3 sightings from separate known bodies. The 3 cone-shaped surfaces intersect and establish a point of position. Actually, throughout the flight, Earth-based tracking information will be used to correct or supplement onboard navigation, so long as it can supply sufficiently accurate data. But as the spacecraft nears the target position, millions of miles from Earth's tracking stations, the astronaut will have to rely to a much greater extent on his onboard navigational equipment. Any backup information from Earth would take 12 minutes to travel the 134 million miles that separate them. He will determine the exact location of his craft with respect to the planet, using sextant sightings, this time between the target planet and known stars. Now he can calculate the final velocity changes that will put him in a precise parking orbit around the planet. Once determined, these velocity changes are applied, and an orbit around the planet is attained. The astronaut will then use his sextant to track landmarks. This confirms his parking orbit and determines its characteristics, permitting him to plan a descent trajectory. In all space operations, man's tools are of utmost importance. They consist of information-gathering devices, both optical and electronic, time-keeping devices, and computers. For manned space navigation, the information-gathering devices are the most varied. They include sextants, or other optical instruments, to measure angles between celestial bodies, onboard radar and other electronic equipment for position determination and tracking, Earth-based radio and radar for precise distance and velocity measurements, and inertial sensing and measuring equipment to provide a reference frame for positioning the vehicle during mid-course correction and to control the corrective maneuvers. Accurate timekeeping and time recording are done electronically to an accuracy of 1/10,000,000th of a second. The computers, onboard and Earth-based, use both stored information and that furnished them by the measuring and sensing devices. They process at a high speed the large number of involved calculations necessary during all phases of a journey. They can solve in seconds problems which would take an experienced navigator an entire voyage to calculate. The National Aeronautics and Space Administration is engaged in the design and development of these devices and at the procedures and techniques for their use. Studies are underway to determine what navigation functions can best be performed by man in space and which function should be automatic or Earth-based. Automatic onboard star tracking equipment developed for unmanned spacecraft will be available to supplement manned equipment. Deep space tracking equipment and methods are now so accurate that spacecraft can be guided to the moon and the near planets with remarkable accuracy. For example, Mariner 2, on its mission to Venus, traversed 180 million miles of space and was placed within 12,000 miles of its target center. This is like shooting at a moving target from a platform that is moving and rotating at a range of 1 mile and hitting the target 4 1/4 inches from dead center. Later, Ranger 7 hit the moon within 8 miles of its aiming point, an 1.5 inch miss at 1 mile. Ranger 9 came closer, impacting only 2 3/4 miles from its target center. Mariner 4 came even closer. Traveling 325 million miles, Mariner 4 swept past Mars within 2,000 miles of its aiming point. And the very first surveyor, Surveyor 1, soft landed on the moon within 9 miles of its target center. A remarkable first attempt. These historic space flights are great technological achievements. They're skillful demonstrations of the reliability and accuracy of Earth-based tracking techniques. But we're still working on the considerable problems of landing on a planet within an accuracy of 10 miles. At the same time, even more effort is being directed toward simplification of both equipment and methods. In manned flight, studies are underway to determine how onboard and Earth-based systems can best work together with the aim of reducing onboard equipment as much as possible. We're constantly improving our knowledge of the planet's masses, their orbits, distances from the sun, so that trajectories can be computed more accurately. We are developing trajectory equations that can be solved by simplified computers, which will still provide navigational data to the degree of reliability needed for manned flight to the planets. Development of new optical techniques for angular measurements are being explored. These may enable the navigator to get accurate information with handheld sextants. Our knowledge is constantly being increased by missions like Gemini. In practicing, we'll gain experience in measuring angles, distances, and relative velocities, and in determining the changes needed to attain specific trajectories. From actual experience, we may be able to make improvements in future systems that we cannot now foresee or predict. Systems development in our most ambitious project to date, the Apollo moon flight, is well underway. The guidance and navigation station aboard the Apollo is equipped with a scanning telescope, a sextant, a digital computer, and an inertial measurement unit. Attitude and guidance controls can be operated directly by the navigator or automatically by the computer at the direction of the navigator. This complete system permits all navigation for the lunar journey to be performed on board, independent of Earth-based tracking or computing facilities if necessary. The navigator will make repeated sightings to confirm his position and trajectory. However, throughout the entire lunar trip, he will have Earth-based tracking information available for use in his own computer. This is how the onboard equipment works. The line of sight of the scanning telescope is fixed to the spacecraft. Looking through this scope, the navigator acquires the Earth and a selected star. He maneuvers the spacecraft until the Earth landmark is centered at 0. Rotation of the telescope reticle till it falls across the star also turns the sextant. He notes the angle of the star and sets the sextant at that angle. Now, looking through the sextant, both images will appear enlarged and superimposed. When they are lined up, he pushes the mark button. This feeds the precise time and angle information into the computer. The computer also receives Earth-based tracking data, which when combined with the observed data, keeps the navigator informed of his current position and actual trajectory. The navigator instructs the computer to make the necessary trajectory correction. It determines the exact amount and direction of thrust needed to accomplish this correction. The inertial measurement unit furnishes a sense of direction to the computer, enabling the spacecraft to be correctly oriented. The rocket is fired. The inertial measurement unit measures the acceleration, feeding this data to the computer. When the desired speed change is accomplished, the computer cuts off the engine, and now the spacecraft is on its corrected course. More than one correction may be needed. As the moon is approached, sextant readings will be made between known lunar landmarks and appropriate stars to determine the final course correction. Both onboard and Earth-based computers determine independently what maneuver is required to place the Apollo craft into a lunar orbit. The familiar landmark tracking technique is then used to confirm the parking orbit, putting man for the first time in a position to land on extraterrestrial ground. The navigational experience gained in the Apollo program will contribute information needed for trips of greater complexity. For man is not content unless he's pressing himself to the limits of his knowledge or beyond.